Hello, good morning. So today we are continuing our discussion on Dinnerweight-Hartenberg notation, and perhaps you have now control over the fundamentals, right? And today I am going to discuss again how to fix up the coordinate frames, and then um, let us solve a inverse kinematics problem, which is very state of the art problem. Okay? So this is how coordinate frame are to be assigned. This is the say this is my one link, this is another link. So it could be there could be another link, okay? Another link, which could be connected with this. Okay. Okay. And this could be connected with another link, and so on and so forth. So whenever you see, so this is an intermediate link, right? I and I minus 1. This is I plus 1 link. Similarly, I minus 1 it could be. So it's a serial kinematic chain. So whenever you see such join, no, you just need to just draw the axis. Infinitely large axis you can draw, okay? That will be your z axis, okay? This is a revolute type of joint. So z axis will be, so zi will be in this direction, zi minus 1 will be in this direction, as you know. So first of all, your objective is to identify joint axis, and then draw the axis, and then identify the common normal between them, between two adjacent joint axis, z axis, okay? So for example, I minus 1, what will be the common normal? If they are not intersecting. If they are intersecting, then the common normal length will be 0. If they are not intersecting, then there will be one unique, and if they are not parallel, if they are parallel again, the two joint axes Z1, Zi minus 1 are parallel, then of course there will be infinitely large common normal, right? And any one you can take. But other than that, there will be unique common normal. What is that common normal? Which will be perpendicular to Zi minus 1 axis as well as perpendicular to Zi axis. Okay. Similarly, what will be the common normal between this axis I plus 1 and I? This is the common normal, which is perpendicular to both the axes. So this is the way you determine the common normal, okay? And where will be the origin of the coordinate frame? So the rule is whenever you find a common normal and wherever it is intersecting z axis, that will be your origin. So, and assign x axis along the direction of the common normal. So x is known, z is known, right-handed orthogonal coordinate frame, y will be automatically known, okay? So you can assign coordinate frame x in the direction of the common normal. So that means x I minus 1 will be this, and origin of the I minus 1 frame will be here. Similarly, origin of the ith coordinate frame will be here, and you see this is your xi, okay? So this is very much well understood now. That is the way you assign coordinate frame. Now if of course these two adjacent z axes are intersecting, then where will be x? X will be perpendicular to the plane containing z and y, okay? So that will be the, if the common normal length is 0, and this will happen if the axes are intersecting, okay? So this is precisely, it is telling that assign xi, that's a unit vector, right? Or cap means unit vector, xi axis pointing towards the common normal, or if the axis is intersecting, assign xi cap to be perpendicular to the plane containing the two other axes, z in this case z and y. Now, you see, assign yi to complete the orthogonal coordinate frame. Also, of course, even if y is not known, then x axis will be perpendicular to z axis. Okay, perpendicular to z axis. Sorry. Now is important issue is, okay, these are all Venn serial kinematic chain, but how about zeroth link and last link? So assign the reference coordinate frame or zeroth link to match first link, and similarly for last link n, choose an origin location and assign xn cap direction freely. But what is my aim? Aim is make maximum number of linkage parameter to be 0, because that will computationally will be efficient, right? So another practice problem we are taking, you see, this is unlike the other practice problem where we had only 2 link. Here I have added another link, 3 link. Okay, this is the 3 link, planar 3 link. Then the pose, that is position plus orientation. Pose can be captured by this gripper. Suppose I have now a plate like this. So gripper can actually orient its pose because it has now 3 degrees of freedom, and 3 degrees of freedom is needed on a plane. Okay, so and what are the rules of assigning coordinate? Same as earlier. You see, this is 0th coordinate frame. Okay, and make ith coordinate frame origin same, so as most of the link parameter will be gone. So I have put our first link here. So this is 0th link. You get my point, right? So you can refer also our textbook, Craig's textbook. So you can see how to direct x. X will be directed towards the direction of the common normal. Common normal actually is the characterized in the link length, and here it is planar, and all the z axes are perpendicular to the plane of the board. They are parallel. Okay, so anywhere you could figure out this, and I am pointing x in a convenient way in this direction. So x1, okay, the unit vector x1 cap, y1 cap, z, and then z1 is actually perpendicular to the plane of the paper or the display here. Okay, so you understand, and then join 2. This link's body coordinate frame is 2 x. So again, x will be directed in the direction of the common normal, perpendicular to the axis y, and common perpendicular both x and x2 and y2 is z2, which is perpendicular to the board. Okay. Okay. So this is what actually we wanted to tell you. This is, unfortunately, this will be your this x. This is x3. Okay, x3. Because here also we are assuming that the rotation axis is perpendicular to the plane of the board. Now you see, this structure can have a pose now. Pose means position and orientation. Okay, and what is the pose phi orientation? Theta1 plus theta2 plus theta3. This is the pose. Okay, so x. So any point here I can put x, y, and phi. So this will be my input. That means I will instruct robot, go xy and orient your gripper with phi. Okay. So necessarily, you see, we are assuming that phi equals to theta1 plus theta2 plus theta3. Theta1 is measured with respect to x-axis, okay, at any instant, and these are all minded, all function of time. And so this is our mother matrix, I am using it. So first, somebody, means designer, you have designed this structure, physical or mechanical structure. Step 1. Step 2, once you get the design, you assign coordinate frame correctly, following the rule which we have specified earlier. Okay. And next, once you correctly have assigned coordinate frame, next job will be to prepare DH table. So this is called Denovet-Hartenberg table. Okay. So this is the link, ith link. This is alpha I minus 1, that is twist angle. This is common normal AI minus 1, DI, distance between two successive common normal, and theta I is the motion parameter. Now, hold your breath and just fill up the table. So this is very important. Once you assign coordinate frame, filling up the table is very trivial. Okay. Number 1, link number 1. So I am talking about this. Okay. So what is the alpha angle with respect to the inertial coordinate frame? Okay. So link 1 means I am calculating 1 with respect to 0, right? This is I minus 1. So I1 means it is 0. Okay. So with respect to 0, I am filling up the table, this row. So this will be 0. Okay. Because there is no twist angle, right? And then this does not exist, 0. Di does not exist. You see, this is the reason I have kept first link here, not here or somewhere here or somewhere here. You had the liberty to put anywhere to describe the body that is characterized by link length 1. Okay. You got it, right? So this is your L1, this is your L2, this is your L3. So these are your link length. Huh? Okay. So, okay. That's so then you come to link 2, and then you see alpha again will be there is no twist because all the z axes are parallel, so 0, twist angle is 0. And what is the common normal length? L1. Okay. And what is the distance between two successive common normal? It is 0, and there is theta 2. Similarly, for this coordinate frame theta 3, the alpha again 0 because all z's are parallel. And what is the link length? L2, this 0, and this is theta 3. It's very simple planar manipulator. Okay. And from here, once you have done this correctly, then it's a very mechanical thing, means there's no nothing to worry. Step 3 is calculate all the matrices from here. Okay. So how to do that? Read this row, and that will give you T1 with respect to transformation matrix of 1 with respect to 0. So you put all the values here. So theta 1, so cos theta 1 minus sin theta 1, 0, this 0. Okay. Then since this is cos 0 is 1, so sin theta 1, then cos theta 1, 0, 0, because sin 0 is 0, okay, and di of 0. Then this is, since this is 0, this is gone. This is also, since this is 0, this is gone. So this is again cos 0, 1, and this is 0 because di is 0. And then 0, 0, 0, 1. That's it. You have got this matrix. Similarly, come on and read this and put all this parameter here, and to get T2, 1, and you will get this. Similarly, come here and again use this and put all the parameters which is written over here to get this one. So once you get all the individual links matrices, then you are in a position to write down the model, that is the equation of the manipulator. 3 with respect to 0 equals to this, which is a function of theta 1. You see the beauty? It's only function of theta 1. This is second matrix is a function of theta 2. Third one is a function of theta 3. Okay, and if you just multiply these 3 side by side, you will get this. Okay, multiplying 3 matrix. And now, so if this is equals to, say, I am calling it x, okay, I am calling it y, okay, and since this is 0 because I am considering a plane, now I have defined a point here, a pose here, x, y, and phi. It's no more a point, it's a pose, means it has orientation, okay. That means it could be something like this. So this point is xy, and this phi is the angle with respect to z axis, which is perpendicular to the plane of the board, okay. So suppose this is there, and I am trying to solve inverse kinematics problem now, okay. So I am just last slide, from the last slide I am getting x equals to L1 cos theta 1, you see. This is equals to this one, px, which I am calling x, is equals to this. Py, which I am calling y, is equals to this, okay. So I am writing these equations and then solving inverse kinematic solution. First inverse kinematic solution, you are getting training, very simple, squaring and adding. You see, square plus this square plus twice L1 L2 cos theta 1 plus cos theta 1 plus theta 2. So C theta 1 means, of course, cos theta 1, okay, and accordingly this sin theta 1, that you know, okay. So very simple, you got it, and then after simplification you are getting x1 plus y1 squared equals to this. So you see, in the process directly you could get theta 2, cos theta 2 equals to x square plus y square minus L1 square minus L2 square divided by twice L1 L2. Now if somebody has given you the robot or you have designed, so L1 L2 they are all fixed geometrical parameter, x y are given point, are known point, right? You are asking robot to go there, so cos theta 2 will be this. Is a function of what you are commanding plus the geometrical parameter, as simple as this. Now this tiny relation also gives you a very interesting constraint. You see, cos theta can be, value can be -1 and +1, value remain -1 and within -1 and +1. So this has to be within -1 and +1. So whimsically you cannot ask the robot to go somewhere, okay. So as soon as you give x1 value, xy value, it will be computed and it will be seen, it will be checked whether it is, so this is the working range of the robot, okay. So if it violates this constraint, it will tell unreachable point, okay. That's great. So now once you got this, then you can get sin theta 2 also just by using this formula, plus minus root over of 1 minus cos square theta 2, and therefore solution of theta 2 will be, I told you 8 and 2 function I need, 8 and 2 sin theta 2 comma cos theta 2. That's the way we write. So in the process of solving inverse kinematics, first you have got theta 2, not theta 1, okay, by doing this. Now let us see how theta 1 can be obtained. I am rewriting now same earlier equation, x equals to this, y equal to this, and here you see now theta 2 is known to me, that's why I am collecting L1 plus L2 cos theta 2, you see, L1 plus L2 cos theta 2 into cos theta 1 minus L2 sin theta 2 into sin theta 1. Why I wrote like this? Because I know that this is already known to me, and you see this is I am calling some parameter because L1 is the link length, cos theta 2 already you have got theta 2, okay, so this is known, so this is a constant now. Once you get theta 2, this is constant, okay, and I am putting L2 sin theta 2 equal to K2. So now this is taking this form, okay. Similarly, same thing, rearranging I am getting in this form, okay. Now I have got another, these two equations I need to solve for theta 1, okay. So I will apply separation of variable principle, again first year engineering math. It's very simple. I am substituting K1 equals to R cos alpha. So alpha and R I have imported some variables, okay, and k2 equals to r sine alpha. You can do the other way around also, and you will have to maybe work a little more, but you will end up the same solution. So r will be equals to k1 square plus k2 square under root. These values are known to you already, okay. And then you can calculate alpha. Cos alpha will be this, sin alpha from here will be this, k1, k2 known. The moment you know k1, k2, alpha is known. 8 and 2 in terms of again 8 and 2 function, okay, k2 comma k1, okay. So from 5, 6, so again you are getting from here. Now I am putting these values. So r cos alpha cos theta 1 minus r sin alpha sin theta 1 equals to r cos of alpha plus theta 1. Okay. Similarly, r sin alpha plus theta 1. So that gives you x divided by r equals to cos of alpha plus theta 1. Similarly, y divided by r equals to sin of alpha plus theta 1. From 8 and 9, you are getting alpha plus theta 1 equal to 8 again in terms of 8 and 2 function, y by r comma x by r. So when you make arctan computation, this divided by this, that means r cancels out. 8 and 2 simply y comma x. Now you got theta 1. What is theta 1? Theta 1 equals to this minus alpha. Alpha equal to, you have got this, okay. K1, K2 already known the moment you know theta 2, okay. So now theta 1 is also known in terms of 8 and 2 function. So once you know theta 1 and theta 2, you can calculate theta 3, you see theta 3, theta 1, theta 2 known, pose actually phi will be equals to phi minus theta 1 minus theta 2. The moment I will give you phi, x, y and phi will be given, right? So theta 3 is known to you. So in that way, in analytical form, you can get theta 1 and theta 2 plus theta 3. So this is very elegant way of solving, and more or less this kind of technique you will use everywhere in solving all robot inverse kinematics problem. Okay. So have fun. This is very simple. I hope you understand. If not, then come to the discussion forum or write comment. Okay. I will try to clarify. Okay. This is very elegant, very important. Now you know how to compute the inverse kinematics solution for any given robot, okay, methodically, starting from attaching coordinate frame, drawing DH table, generating the individual matrices, and then writing them together, figuring out the manipulator equation, manipulator model rather, and left hand side is known. This is the way right hand side, which is function of theta 1, theta 2, theta 3, has to be calculated. And incidentally, this is called analytical solution, because you see everything is very precise, very there is no numerical iteration here, okay. And this kind of solution normally we prefer in robotics. With this, thank you for your attention. Have a nice day. Bye bye. So next time we will take more example, and I will show you similar kind of but different structure, so that you will never forget and you will be having confidence in developing the manipulator solution. Once you get the solution, you have everything. Theta 1, theta 2, theta 3. For forward kinematics, once you have the this kind of thing, no, you can run forward kinematics. That means you can generate this by running loop, 3 loop, theta 1, theta 2, theta 3, okay, theta 1 outer loop, theta 2, so nested loop, theta 3. So every joint will have some range. It cannot be 0 to 360, okay. So that range you can put over here, okay, range R1, R2, okay, R1, R2 range, okay. Then different range, R1 prime, R2 prime, then R1. So if you know the ranges, you can calculate this matrix, okay, and that will be actually huge data, and that's called Forward kinematic solution give you you can calculate the working envelope of the robot using forward kinematics. Using inverse kinematics, you can command the robot to go somewhere, and eventually we can control it. Okay, so slowly and steadily you are learning all these things. Have a nice day. Bye bye. Stay safe.